because that we will require to understand what happens when we have a three-phase full bridge thyristor converter, as normally we do have. Okay, so this is the structure of this three-phase full bridge converter. It is made up of 6 thyristors, and these thyristors are labeled as they are here for the reason that this is a sequence in which they conduct 1, 2, 3, 4, 5, and 6, and then 1 begins to conduct. Okay, so that's so what we see here is that these 3 thyristors, 1, 3, and 5, they make up the positive group, and for sake of simplicity, first we will neglect the AC side inductance, which is never negligible, but this is for analysis purposes. Let's start there, and we'll see how this 3-phase AC coming in gets converted into a DC voltage over here. All right, so having neglected these AC, these inductances on the AC side, we can draw the 3 thyristors making up the positive group in this manner, where their cathodes are connected together to a common point P here. Similarly, in the bottom group, we have these thyristors 4, 6, and 2, and we can draw them in this fashion, and where their anodes are connected together to this point N over here. And in between, we have the AC side circuit, and let's just represent it by current ID here, and let's assume it to be constant for now. So ID is purely a DC current, we'll assume at the moment, but it's not too far from the truth, okay, in actual HVDC systems. And V sub D is the voltage between point P and point N shown here. All right, so we'll look at these waveforms in the next couple of slides. So let's assume that we are operating this 3-phase thyristor bridge as if it's made up of diodes. Okay, what that means is that we are not introducing any delay angle into the conduction of these thyristors, so alpha is equal to 0. As soon as the voltage becomes a forward polarity across this thyristor, it will begin to conduct because the gate pulse is there, because we are not delaying it by assuming alpha is 0. That's how these waveforms are drawn. The other thing we have assumed that on the AC side, there is no inductance. So L sub S is 0. So what we see here, we have these 3 phase voltages coming in, VA, VB, and VC. And if we go back to this this arrangement, this type of redrawing of the full bridge converter, at any instant of time, only one of the 3 thyristors here would conduct. And the one that will conduct has its anode connected to the highest voltage, okay, out of these 3. And the other 2 would become reverse biased. Similarly, in the bottom group, this negative group, only one of the 3 thyristors would conduct, and the one which has its cathode connected to the most negative voltage would conduct, and the other 2 would get reverse biased. So that's something which we have to remember. In the upper group here, where cathodes are connected together, the thyristor with its anode connected to the highest potential would conduct, and in the bottom group, where the anodes are connected together, the thyristor with its cathode connected to the most negative potential would conduct, and the other 2 would get reverse biased. So that's what is happening here, and we see that when if you look at this 60-degree interval here, right here, so in this interval, phase A, the thyristor 1 connected to phase A would conduct because voltage of phase A is maximum, and at this instant, B, which is connected to actually I should say B is connected to, this is phase B, so it's connected to 6. So here, this is connected to thyristor 6. So phase, the thyristor 1 connected to phase A would conduct, and thyristor 6 connected to phase B would conduct. Then if you look at this 60-degree interval, again, B is, 1 is going to keep on conducting because phase A has the highest voltage, but now this phase C has the least negative potential, most negative potential. So in this case, 2, which is connected to it, would conduct. And then if you keep going on here, now instead of 1, 3 would take over, and then 2 is still conducting. Okay, and then if you go here, what you'll see that 3 will keep on conducting, but now A has the most negative voltage, and number 4 is connected to A in the bottom group. So 4 would conduct, and then if you keep on going, 4 would keep on conducting here, but at this point, 5 will take over, and so on. And then 5 will continue here, but in the bottom group, since B is most negative and 6 is connected, so 6 will come on here. So what we see here is, that sequence I talked about. The conduction is 1, 2, 3, 4, 5, and 6, and then repeats. And that's why we very carefully labeled those thyristors as we did. Okay. And what is the DC side voltage VD? That's the potential between, which is the difference between the potential at point P, and this upper curve is connected to point P, and the bottom curve is connected to point N. So the difference between the top and the bottom waveforms is the DC side voltage, and you can see that it's really made up of these line-to-line voltage segments, as we see here. And we can integrate, we just have to integrate over a 60-degree period, because this waveform is repeating every 60 degrees, although there is a different line-to-line voltage that is appearing across the DC side, but we just, to get the average, we just need to look at a 60-degree interval. And from there we see, if we do that, that the average voltage, VD0, is made up of the average line-to-line voltage times this factor here. So this is about 1.35 times V line-to-line here. Okay. So we looked at the voltage waveform on the DC side, but how about the currents on the AC side? So let's look at those here. I mentioned to you that 1 is conducting here, 3 is conducting here, and 5 over here. Then 6 here, 2 here, and 4, and then 6 over here. Okay, and so you can see here that when the DC side current is purely DC, as we are assuming here, I sub D. Okay, and here 1 is conducting during this interval from here to here. So I sub A would flow as shown here. And similarly, when 4 is conducting here, which is also connected to phase A, and so 4, because of 4, I sub A would be like this here. So what we see here is that any of the phase currents, it's made up of these 120-degree pulses. In the positive when the top thyristor is conducting, and negative when the bottom thyristor is conducting. And for this in-between 60-degree interval, no current flows through phase A. And the same thing we can say about phases B and C. The waveforms are just 120 degrees displaced with respect to each other. All right, and this is all is happening assuming alpha is 0, and also the AC side inductance is 0. All right, Now we introduce another variable, which is the delay angle alpha. Previously, thyristors were behaving like diodes, but now we introduce a delay angle alpha with respect to their instant of natural conduction. That is, the instant at which they would have started to conduct if alpha was 0, that is, if the thyristors were replaced by diodes. Okay, so and we can see here that thyristor 1, which is connected to phase A, should start conducting here. But we are introducing, with respect to this instant of time, this delay alpha right here. So the gate pulse is coming here at this point over here. So long as we are not allowing thyristor 1 to conduct, this current has to flow through the thyristor which was previously conducting, and which in this case was thyristor 5 connected to phase C. So the voltage waveform at this point P, instead of going up at this instant of time, it follows the waveform of the phase C voltage up to this point. And then when we apply the gate pulse to thyristor 1, immediately thyristor 1 begins to conduct, assuming no inductance on the AC side, and then the waveform for point P would follow that of phase A voltage. And similarly, at this point, thyristor 3 connected to phase B should have started conducting, but we are introducing the same delay here. So A keeps on conducting up to this point, and the gate pulse comes to thyristor 3, and the voltage jumps to phase B over here. And same thing for phase C. And whatever is happening on the positive side is happening to this bottom negative group also. So you can see that the waveform that we have, maybe I should erase the ink that, on the top group, the voltage waveform would look like this. Okay. All right. And in the bottom, the voltage waveform would look like this here. Right. So this is how we can exercise control over the average DC voltage coming from this thyristor converter. So in this, what has happened is that every 60 degrees, so many volt seconds here shown shaded are hashed over here by this area AU. So many volt seconds are lost every 60 degrees, and we can compute that, and that is a reduction in the DC side voltage. There is no power loss associated with it. That's very important to recognize. There's we are not losing this power as heat, but it's the reduction in the average DC side voltage, and that average here is computed first by computing this area in volt seconds and dividing it by pi over 3, because this is happening every 60 degrees. And if we do that, then this is the result here, and then we can compute what is the average DC voltage in the presence of this delay angle alpha as the one without any delay angle when the alpha was 0 minus this drop over here. And that turns out to be this expression here, which is 1.35 V line to line cosine alpha. All right. So it clearly shows the effect of introducing this delay angle alpha here. And in fact, we can make this alpha go more than 90 degrees. And then what happens is that the top waveform appears, what used to, I shouldn't call it top, the voltage waveform for point P appears in the bottom, and the waveform for point N appears to be on the top. And recall that V sub D is Vp n minus Vnn, and therefore, where this n is the AC side neutral. And so clearly you can see that if this waveform is at the bottom and this waveform is at the top, the average DC voltage would be negative. Okay, so that's what happens in these thyristor converters, that we can go in what we call an inverter mode, and we'll see this very clearly. And certainly the current waveforms would also be then displaced by this angle alpha as compared to before. So this is the delay that occurs in all these current waveforms. All right. So let's look at the effect of this delay angle. So here I'm plotting the average DC voltage across this thyristor converter. So let me just draw it like this here for our reference purposes. So this is ID, and this is VD here. Right, it's defined like this. So you can see that as we increase alpha, this DC bus voltage begins to decrease up to this 90-degree value, at which point it goes to 0, and beyond that it becomes negative. Okay, if you keep increasing this delay angle alpha, and so this alpha is between 0 and we don't go all the way up to 180 degrees, because something bad would happen. It's called commutation failure, something like 160 degrees or so. So that's the plot. And in this case where we have neglected the AC side inductance, we can see that we are in the so-called rectifier mode of operation, because in this mode, both we have to recognize that the current in these thyristor converters cannot reverse. So the current is unidirectional, and that's shown in this plot over here. Okay, but the voltage, so long as alpha is greater than 90 degrees, less than 90 degrees, this voltage is positive. Okay, so we are in this region over here, and the power that is flowing is this way. Yeah, so that's we are in a rectifier mode, because the voltage is positive, current is positive. So if you define the power this way, it is positive. But if we go to a value of alpha greater than 90 degrees, then this V sub D has become negative, right? And current is still positive, so the power is negative. P is negative here. So if you define the power as shown here, the direction, then this P is negative. That is, it's flowing from the DC side to the AC side. And that is called the inverter mode of operation. Okay. All right. So having covered that with zero AC side inductance, which is practically never the case, we should take the next step and try to see what happens when we have AC side inductances present. And if we do that, then without the AC side inductance, the voltage, as soon as we apply a gate pulse, would have jumped, and this curve would have been followed. But because of the AC side inductance, the current cannot change from one phase to the next instantaneously. So there is an overlap, and during this overlap period, this is called commutation interval, where the current is commutating from one phase or one thyristor to the next. Both of these thyristors conduct, and basically two of the phases are shorted. And on the AC side, on the DC side, I should say, at point P, for example, the voltage waveform is somewhere in the middle of this waveform and this waveform here, right here. So if you think of that as this being the middle of this and this, then this additional area is lost every 60 degrees. Okay, so that area, let's indicate that indicated as A sub U, and that area is from this alpha where the gate pulse comes, but this is where alpha plus U is where the current has shifted from one thyristor to the next. So we can compute this area A sub U, which turns out to be this here. So that is, you can also see that from basic principles, that certain volt seconds are needed for the current to commutate through an inductor. It's going from 0 to ID in one of the phases, and is going from ID to 0 in the other phase. Okay, so that's what this is indicating. And the average voltage that is lost is this area divided by pi over 3, because that's it's happening every 60 degrees. So the average reduction is this much, and this we had computed earlier, and now if we include this reduction as well, the bottom line is that in the presence of AC side inductance and the delay angle alpha, we get this expression as we see here. So that's a complete expression for a so-called three-phase full bridge converter. All right. Now, the other thing we should recognize, we have been concentrating so much on the DC side that we should not forget what's happening on the AC side. So if you look at the AC side currents, first of all, we saw them as looking like this here, right? But if you think of their fundamental and represent them as a phasor, so this is the phase A voltage, and this is the phasor which is representing the fundamental frequency component in the AC side phase currents. This current would lag behind this phase voltage by this angle phi1, where phi1 we can show is approximately equal to the delay angle that we introduce plus this commutation interval where two thyristors conduct and simultaneously divided by 2. Okay, so that is basically the phase angle by which it's delayed. Here we are showing it in the rectifier mode, here in the inverter mode, and you can see that the reactive power that is drawn from the AC side is given by this expression. So you can see that reactive power is always lagging in these thyristor converters, whether it's operating in the rectifier mode or in the inverter mode. That is, this thyristor converter always requires reactive power to be drawn from the AC system, regardless of whether the power is flowing from the AC side to the DC side or vice versa. But reactive power is always drawn as an inductor would draw from the AC system. And here is an example of a HVDC transmission system which comes very close to Twin Cities, Minneapolis, St. Paul, where we are located. There is a mine mouth plant in North Dakota, and so this line at plus minus 400 kV comes to, it's a more than 300-mile long line, very close to the Twin Cities. Over here, the power level I think is about, I'm not sure it's listed here, but it's over 1,000 megawatts. Okay, and the distance is listed here, I think 700 something kilometers here. All right, to find power, we have to just take 400 kV times 1250 amperes times 2. Okay, because we have 2 poles here. All right, and other thing we have to recognize that since the current waveform is not perfectly sinusoidal, there is a great deal of filtering that is required, and that is shown in this figure right here, the filter yard, and also to provide reactive power, which otherwise would be drawn from the AC system. So some these filters provide some of this reactive power. Okay, and also on the DC side, some filtering is needed. Otherwise, there could be interference with communication lines and so forth. So this brings us to the point why we need a 12-pulse operation. We saw earlier that we had a YY connected transformer, and then we had a delta Y connected transformer. Okay, and The reason for using that is that these connections are in parallel on the AC side and in series on the DC side. So the currents drawn from each of these, they add up to form the current drawn from the AC side. And so for YY connection, the waveform is shown here. For a Y delta connection, the current drawn is shown here. But when you add these two, the resultant current is coming closer to a sine wave. So by connecting this in so-called 12 pulse operation, we have a somewhat nicer current waveform drawn from the AC side. And when it comes to the DC side voltage, one of these waveforms here, I won't bother to draw it, is for one of the converters. This one is for the other converter. That's why we see here VD1 and VD2, output of converter 1 connected through YY, and output of converter 2 connected through Y delta. And when you add these two up on the DC side, the voltage waveform is looking like this. And the reason it's called 12 pulse waveform is that if you look at this 360-degree cycle of the fundamental AC frequency, line frequency, we have 12 pulses in here. Whereas if you had just used YY or just to use delta Y, we would have only 6 pulses. So that has a much higher harmonic content as compared to this arrangement here.